plenary. We have 7 regions that we're looking at here in Lake Champlain, and I used 6 different models to evaluate the use of these different regions. And some of these regions are pretty well separated by these man-made causeways. So these are rock structures that almost entirely prevent fish movement. It's hard to see, but there's a tiny opening here that's meant for boat passage, but fish also are able to get through there. And so we're able to see if organisms and the simulations are moving between these regions. Now, the main lake regions, there's no causeways out in the middle of the lake, but these are different management regions, so we're able to distinguish the use of these regions for our own interests. And I had this prediction that, of course, if you have a more complex model, it has to be more accurate, right? Because why else would you use the more complex model? So I really thought I was going to go far with that one, and that might be a little bit of a clue as to what we find later on based on the sarcasm you might detect in my voice. So getting into the models that I used, start off with just kind of what you might consider control, the basic model, just based on where these fish were detected. The cartoon here on the right gives an example of this. You can think of the blue circles being our receiver stations. The size of the circles correspond to the number of detections at that location. The black path represents the actual path taken by the fish, and the gray box here might be some area of interest or one of our regions. And so again, that base model, I'll refer to as base, just uses a base residency index. Where did this fish show up and how many times did it show up there? The next one, the last observation carried forward technique. So this fills in gaps between detections. So say I have a fish that's detected here, and then it's not detected for a while until it's detected at this site. It's going to say that this fish, we're going to assume that across time it was at that last observed site until it's next observed. So it's filling in these time gaps. The third technique uses centers of activity, and for our project here, we use 60-minute centers. So for every 60 minutes, it creates a weighted average position. So if we think about this being a 60-minute window, and we've got more detections at this site than at this site, so that average position is going to be slightly closer to that larger circle. So we do that every 60 minutes. Next, we use an interpolation model. So this incorporates both linear and nonlinear interpolation. So you can think of that as just filling in the gaps with positions for where the fish was, or for where an organism might have been detected. If you're familiar with acoustic telemetry, and if you use the GLaDOS package, you might be familiar with the interpolate path function. It's typically used for making animations. And so here this is the first time that this is being used to describe actual animal distribution rather than just using it for animation purposes. And so it's, here you can kind of imagine they are linear paths here, but if we had land that might jut out into the track, it would go around the land to better represent an actual path rather than having it going across that land. That's why it's very common to use this with animations, because you can see where fish moved while staying within the water body. And the next 2 models are both these Brownian bridge models, or dynamic Brownian bridge movement models, which similarly fill in these time gaps, but they do it based on probability, taking into account the amount of time between those gaps. And what's different with this type of model is you get this utilization distribution. So just what's the probability that an individual occurred at any location based on where it was last observed, where it was next observed, and the amount of time between those spaces. And what's interesting here is you can see now we start to get into that area of interest. So just getting a little bit more complex as we've gone from the basic model down to the Brownian bridge model. This is called the MOVE model because it used an R package called MOVE. We had a separate Brownian bridge model that used a package called RSP, so naturally that's the RSP model in this study. And we had 5 different criteria that we were using to evaluate the performance of these different models. We can actually know what the use of the different regions were by the simulations, and then see how accurate the models predicted those uses, the use of those regions. So the first thing that we looked at was it's a mean weighted occupancy error. We can think of it as just, if you take all the regions that a fish used, how much did it use that region in reality, and how much did the model say that it used? Take the difference of that, and that's your error, and then we weighted that based on the amount of time that an individual actually spent in that region. So just think of it as the higher the value, the worse that model did, the more error there was, averaged by the regions. Next, just looked at the actual regions themselves and looking at whether or not models overestimated or underestimated the use. So for example here, the red values represent a region that a model overrepresented the use on average, and blue would be areas that are underrepresented by models. Just looking at how poorly or how badly the models did, we just look at the absolute value of those errors. So the previous slide was the actual error, now we're looking at the absolute value of that error. So everything's going to be above 0. How far away was it from being accurate? And then lastly, think of just more general ways that data might be used, looking at the daily region assignment. So across all days, which region was used most frequently by each of these models? And does it represent what was actually occurring? So here's an example here where we have the actual region that was used most frequently for each day, and then predicted from a model, and you can see that for one of those days it was not correct. So we just look across all the days for each of the simulated tracks, for each of the models, and figure out how accurate they were, what was their error. And then lastly, just the total regional occurrence error. So across the entire duration of each simulation, how many individuals showed up at each of the regions, and how close is that to the actual number of simulations that occurred at some point throughout their entire simulated track in those regions. So it's just a simple count. So diving right into the results. So this is a comparison of that mean weighted occupancy error. Again, you can just think of this as the higher the value, the more error, the worse the model. And overall, I would say models typically do well. There's less than 10% error across everything, but it could get pretty high. The highest error we saw was 63%. So that means that on average, this model, for example, had over half the time it was saying this fish was it was predicting the wrong region for that individual track. And we also saw some significant differences here. So the x-axis, these are the different models, and they go from least complex to the most complex, and we see that that interpolate path function from the GLaDOS package actually had the lowest error averaged across regions. It was really exciting. That's not what my prediction was. I thought, the most complex model incorporates those other factors, it would be something that would have a more accurate representation here. So that was exciting to see. We also saw some differences between the two different Brownian bridges. So this shows that the packages that you're using within R can really have a big influence on the interpretation of the data. And the last point there, that both of these Brownian bridge estimates we believe are impaired by large gaps in the detection. So as I mentioned, these models are able to estimate where fish are based on where they were last detected, where they're next detected, and the amount of time between them. And so when you have huge gaps in your detection data frames, there's a lot of places that fish could potentially go. And so these models are influenced by that, and that leads to higher error. So next, just looking at the overestimation and underestimation across the regions. So main takeaway here, you've got the different models, and you can see that there's just different colors. So there's inconsistent error among these models. The only time that there was any consistency was this Missisquoi Bay region and the northeast arm, and that's driven by this the Missisquoi Bay. There were no receivers up there. So of course, if you have no receivers, it's going to be very hard to detect you're not going to be able to detect any fish in those regions, so you're always going to be underestimating how much fish are using those spots. And if you're underestimating in one spot, that means they're going to be overestimating it in another, and that's going to occur in the adjacent region, the northeast arm. But again, we see that this nonlinear interpolation model, or the interpolation model here, is doing the best job. It's got the lowest error. So that was really exciting to see that across our criteria, we're seeing this consistent pattern of the interpolation model performing best. And we looked at this from statistically, and both with the